Hello, welcome to this lecture. In this lecture, we are going to look at few topics that we were not able to cover so far from chapter 2 of the book. So this will be filling gaps lecture. Uh, I will talk about four distributions that we didn't discuss so far, and then we'll look at a new topic called entropy, and then finally Benford's law. Right? Uh, these will be included in three separate lectures, each lecture about 1 hour of length. Right? So we will first start with these four distributions: log-normal distribution, Cauchy distribution, beta distribution, and Laplace distribution. First one is log-normal distribution. Many students directly think that if a certain random variable has a normal distribution, then log-normal distribution is the distribution of the log of x. That's a wrong idea or understanding. Of course, we will not be able to talk about log of x if x is normal generally, because a normal distribution can be distributed between negative infinity and positive infinity. So if you consider log of negative values are not defined, therefore, of course, we cannot talk about log of a normal distribution. So therefore, let's look at what this log normal distribution is actually. So suppose the random variable y has a normal distribution. And suppose x is equal to e to the power x, not the log of x. So y has a normal distribution. We are considering the e to the power y as our x. Then the distribution of x is called the log normal distribution. So it's not the log of a normal distribution, it's the exponential of a normal distribution, which is called the log normal distribution. Now notice that if y has a normal distribution, then y is theoretically between negative infinity and positive infinity. So therefore, if you consider e to the power y, it's going to be greater than 0. So therefore, the random variable x that we consider here is a positive random variable. Or we can say on the other way around, the random variable x is said to have a log normal distribution if log of x has a normal distribution. Random variable x is said to have a log normal distribution if log of x has a normal distribution. If x is equal to the power y, then y is equal to log of x and y has a normal distribution. So therefore, there are two ways to explain the log normal distribution. The first way is, if y has a normal distribution, then e to the power y has a log normal distribution. Or equivalently, if log of x has a normal distribution, then we say x has a log normal distribution. So now let us derive the distribution or the density function of a log normal distribution. Suppose y has a normal distribution with mean mu and variance sigma square, then for any real number x, positive real number, we can define the cumulative distribution function of capital X evaluated at simple x as that is by definition, the probability capital X less than or equal to simple x. But now we know that we are taking x to be e to the power y, therefore it is the same as probability e to the power y less than or equal to simple x. E to the power y is a one-to-one function, therefore, and also it's monotonically increasing function, therefore this statement is equivalent to this statement. This event, e to the power y less than or equal to simple x, is equivalent to the event that y is less than or equal to log of x. Therefore, this probability is equal to this probability. But we know that y has a normal distribution. We are assuming that y has a normal distribution with mean, mu, and variance sigma square. So therefore, this probability statement, I can convert it into a standardized normal. I can write down it in terms of a standardized normal random variable. So what you do is you take away the mean y minus mu divided by sigma. So that side will be z less than or equal to log of simple x minus mu over sigma. Notice here, simple x is a real number. Capital Y is the random variable. Right. So then this statement. So what you have now here is the cumulative distribution function of a standard normal random variable evaluated at this real number here. This real. So the cumulative distribution function of a standard normal random variable is usually denoted by capital pi. So therefore, we can write down this as pi evaluated at this value. So that is the cumulative distribution function of x. So if we want to get the density function of x, we have to differentiate this with respect to x. So therefore, the previous one I didn't mention on this side. I mentioned it as a function of x only, but you can see that it's going to contain mu and sigma square also. So if you write down in the using the long notation, it has to be f subscript x and then evaluated at simple x, but there are two other parameters in the function also. This is how you write down a family of distributions. So you can write down like this with more details. It's greater than 0 here. Then, as I mentioned, if you want to get the density function, you have to differentiate the cumulative distribution function with respect to simple x here. So then you get the density function evaluated at simple x, but it's also going to contain these two parameters. So when you do that, when you differentiate this one, you are going to get the density function of a standard normal distribution, which is denoted by simple pi. So simple pi evaluated at this value, but then you have to multiply by the derivative of this quantity with respect to x, right? Applying the chain rule, right? So that's where this term comes 1 over sigma times x, right? Log of x. When you differentiate, you get 1 over sigma, but there's a sigma 1 over x. There's a sigma 1 over sigma also. Therefore, you get this term. So therefore, finally, you get this density function, right? Because we know that pi is it, right? If I write down this, for example, right? We know that standard normal density evaluated at some value z is equal to 1 over root 2 pi e to the power minus z square over 2. So therefore, what we need is pi at this value. So therefore, what you need is, so this part will be still there. Then 1 over root 2 pi e to the power, this thing square divided by 2. Then you get this quantity. So that is the density function of a log normal distribution. So I have here shown two cases of log normal distribution with mu equal to 1 and mu equal to 2, but sigma is, I have taken sigma to be equal to 1 here. So you can see that these distributions have a very long tail. They are very positively skewed. Right? You may remember we discussed earlier one family which has positively skewed distributions, that is gamma family. And this log-normal family has even longer tails without coming to zero as quickly as even like gamma distributions, right? So if you have a situation where you have uh, few small numbers, possible few small numbers, and then uh, very large but very rare numbers, then in that kind of situations, a log normal distribution may be suitable than a gamma distribution as a model for the density function of that random variable. Right. So now you have another family of distributions which can be used to model positively skewed distributions. So what are the important characteristics of the log normal distribution? Well, we have already discussed that in this case, the random variable is positive, so it's greater than zero. The distribution is positively skewed or rightly skewed. It has a very heavy tail, right tail. Tail means going to the right without coming to zero very quickly. So that means very large observations may occur with a small probability, of course. And then it's useful usually for modeling uh, random variables that have that kind of possible values, large possible values with small probability. For example, income of a randomly selected person in a certain area or town or country. Right? We know that most of the people's income are relatively small, but there are very few people whose incomes are huge, right? So therefore, a log normal distribution may be suitable as a model for the income of a randomly selected person from a certain population. And similarly, weights of people can also sometimes be modeled by this kind of distribution if the population has few excessively uh, uh, weighting peoples. That means with a very large weight. Right? Few people with excessively large weights. And survival times uh, of some products, for example, right? Most of the products may have some relatively small number of years of survival time, uh, but there may be few items which have survival times, quite large survival times, doesn't break down until very long time passed, right? And also financial data, right? Like insurance data, right? Usually the insurance claims, right? The values of insurance policies uh, can be somewhat large, from very small to somewhat large, but there can be very huge policies, few of them. So again, log normal distribution might be suitable as a model for the probability density function of a uh, value of a certain insurance policy. Right. And there's another theoretical aspect. We can show that the mean and the variance of a log normal distribution, if the corresponding normal distribution right? Remember that I have explained the relationship between this log normal and normal, right? So if y has a normal distribution with mean mu and variance sigma square, then e to the power y has a log normal distribution. It also contains the same two parameters, but now in the log normal distribution, mu is not the mean. And similarly, in the log normal distribution, sigma is not the standard deviation, right? They are just two parameters. Uh, but we can find out the expression for the mean or the expected value of x, right? And that is not equal to mu. That will contain mu and sigma both in this case. It's a function of that. You can find out if you really need that expression. You can easily find out from the internet. And similarly, variance of x when x is log normal. Again, it's going to be a function of mu and sigma both, right? Not like in a normal distribution, mu is mu and variance, standard deviation is sigma, right? Uh, so I didn't mention them here because they're just some mathematical expressions. If you want, you can find them out. But I mentioned the median of x here. It's just e to the power mu. It contains mu only, right? If x has a log normal distribution, then the median of x is e to the power mu. And this is important for something that I'm going to discuss a little later, right? So that's why I mentioned here, right? So remember x, if y has a normal distribution with mean mu and variance sigma square, then e to the power y has a log normal distribution. That e to the power y has the median e to the power mu. That's a kind of interesting result, right? But it's not. I mean, it's not. It's not. The mean e to the power of the mean is equal to the mean of log normal. Actually, the median of in the normal distribution, of course, mean and median both are the same. So in that sense, also you can discuss this because if y has a normal distribution with mean mu and standard deviation sigma, then the median of that normal distribution is also mu, right? So in that sense, now y has a normal distribution with, let me write it down. It's kind of interesting result. Uh, so y has a normal distribution with mean mu and variance sigma square, right? So then the median of y is also mu in this case, right? We are considering x to be e to the power y. So what this theorem says is median of x, that is the median of e to the power y, is the same as e to the power mu. So it looks like just transforming, we are just directly transforming the parameter as well, but it's not coming in that way. It's mathematically coming if you find out the median so that we can, how do you find out the median? If you want, suppose median is equal to, say, for example, nu, let us denote the median by nu, then this is uh, nu will be satisfying this probability statement. Probability x less than or equal to nu is equal to 0.5, right? So if you solve this equation for nu, then you will get this answer here, right? But this is interesting, right? Median of x, which is the median of e to the power y, is equal to e to the power mu when x is equal to e to the power y, where y has a normal distribution with median mu, right? Uh, so let me delete this part. But you cannot say that the expected value is of x is equal to e to the power mu. That is not correct. Okay, why? Okay, my pen. Right. So expected value of x is not equal to mu. Or expected, or it is not even equal to e to the power mu. There is some other term coming with sigma. And the variance of x is, of course, not equal to e to the power sigma square or something. So these are not correct expressions in this case. They don't have to be because we have shown earlier when we talked about transformations. I have explained this clearly. Expected value of some g of x, this is not equal to g of expected value of x in general. It will be usually correct only for linear transformations. Right. But this result is important and we will discuss this thing little later. So this is that property actually I want to discuss. An important property, practical property, is that the geometric mean of a sample of data, geometric mean of sample of data can be considered as an estimate for the median of the log normal distribution, right? We know that usually sample mean is always a good estimate for the population mean, right? There are several types of means now. This is usually when we say mean, we mean arithmetic mean. But we are here talking about the geometric mean. How do we define the geometric mean? Geometric mean is defined like this. The product of the terms, if you have several x's, x1, x2, x3 up to xn, then it's a geometric mean is defined as 1 over nth power of the product of the observations. That's what the geometric mean means, right? So what we are saying here is, if x has a log normal distribution, and if you have several observations coming from that log normal distribution, say x1, x2 up to xn, then the geometric mean of those n observations is an estimate, can be considered as an estimate for the median of capital X, or the median of the log normal distribution. Right. So in order to see how it becomes a good estimate, let's consider a random sample, capital X1 up to capital Xn. These are the variables that we talk about, right? Let's say capital X1 up to capital X is a random sample, and let's say simple X1 up to simple X is and it's a realization of this random sample. That means simple X1 is an observed value of capital X1. Simple X2 is an observed value of capital X2, and so on. That's what we mean by a realization. Now, let's consider yi is equal to log of xi for I from 1 to n, and simple yi is equal to log of simple xi for I from 1 to n, right? Just log transformation. Now, we know that if x up to x1 up to xn are log normal, then the log of x are normally distributed. Log of x are normally distributed, right? So that means these random variables, y1, y2, y3 will have IID normal distributions. Yi are normally distributed with mean mu, say, right? So therefore, we can say expected yi is equal to mu for I from 1 to n. So therefore, as I mentioned, we can consider y bar, observed value of those y values, right? After transforming with log transformation, we get y values. So the sample mean of those y values, y bar, can be will be very close or around this mu, because expected value of yi is equal to mu. Therefore, yi is distributed around mu, and we know that when n is relatively large, of course, y bar is going to be close to mu with a high probability. So therefore, we will say y bar is approximately equal to mu, right? This approximation will be more and more accurate if n is large, right? So we have an approximation. So if you take the exponent of this both sides, right, you can say e to the power y bar is approximately equal to e to the power mu, right? But we mentioned that e to the power mu is actually the median of the log normal distribution or median of capital X. Right? So therefore, what this says is that we can consider e to the power y bar as an estimate for the median of X or median of the log normal distribution, right? E to the power simple y bar will be a value, right? That value can be considered as an estimate for this quantity. And if you replace the simple y bar by capital Y bar, you get a random variable e to the power capital Y bar, then can be considered as the corresponding estimator, right? So we have already seen that e to the power mu is the median of X. So as I mentioned, we can consider e to the power Y bar as an estimate for the e to the power mu, which is the median of X. But what is e to the power y bar? E to the power y bar is equal to e to the power 1 over n, the summation of log xi, right? Because each yi is equal to log of xi, right? So this is the expression. Now you can, with simple mathematics, you can see this is the same as this expression because here e to the power and then there are some log terms with the summation, right? So with simple mathematics, you can see that this is the same as this. But what is this? This is the geometric mean of those original observations of x1 up to xn, right? So what does this tell you? That we have told that this quantity can be considered as is an estimate for the median. So that means the geometric mean of the original observations of x's can be considered as an estimate for the median of the log normal distribution or the median of the random variable x. So that is an interesting result to remember, right? Now, as I mentioned at the beginning, and as we saw from the graphs and so on, the log normal distribution is very, very positively skewed. So therefore, if you want to look at the range, for example, of x values covering a given probability, but with the shortest interval, that is the tight confidence range, right? Uh, for this distribution, actually, tight confidence range will be much better to look at than the symmetric confidence ranges that we look for, usually normal distribution or some symmetric distributions, right? Especially tight confidence range is more meaningful or more useful for this kind of distributions like gamma and also log normal. So if you want to ever find out a region covering, for example, 95% probability of a given log normal distribution, it's better to find out the tight confidence range rather than getting an interval where the area left to the lower limit is equal to alpha over 2 and area above the right limit is equal to alpha over 2, which are called the equal tail probabilities, right? That's what usually people consider because they can be obtained very easily using some tables or using even R, right? In this case, you have to ask just Q log norm, uh, QL norm, in this case, log norm, QL norm, alpha over 2, and then QL norm, 1 minus alpha over 2 will give you the equal tail confidence range. But you better look at the tight confidence range instead of equal tail confidence range, because because it's a skewed distribution, very very skewed, right? So that is a brief introduction and a discussion about its properties, and especially a different estimate, right, for the median, right? So usually if you want to estimate the median of some distribution, generally, you will just look at the sample median, right? If you want to estimate the population median, you people tend to look at the sample median, consider the sample median as an estimate. But in this case, we saw that if you think that the log normal distribution is a suitable model for the density function of your random variable, in that case, the geometric mean will be a much better estimate, and of course, the corresponding random variable as an estimator for the median of that random variable, right? So now we are going to look at the next distribution called the Cauchy distribution. In the class, I have mentioned several times about this distribution as one particular distribution comes up in some examples where some theories don't apply, right? Remember when I was discussing about the central limit theorem, I told you that usually the standard central limit theorem uh, considers an IID random variable from a distribution with a finite mean and finite variance. And then central limit theorem says that the sample mean, the distribution of sample mean, of course, the theorem says that it talks about the distribution of the standardized sample mean after taking away the mean and divided by the standard deviation, converges in distribution to standard normal distribution. Right? But that theorem is valid if the data or random sample is coming from a distribution with a finite mean and finite variance. And at that point, I mentioned that there are situations where the random variable or the distribution doesn't have a finite mean. Mean doesn't exist, and thereby variance doesn't exist. And Cauchy distribution was mentioned as an example. Right, so that's what we are going to look at now with a little bit more details. Right, so the Cauchy distribution generally has only one particular distribution like this. The density function is given by this. This density function is symmetric around zero. Right? Symmetric around zero. The x values can go from minus infinity to plus infinity. And also when we are talking about the t distribution, also I mentioned that there are several large number of t distributions with different degrees of freedom. And I mentioned that in particular, t distribution with 1 degree of freedom is called the Cauchy distribution. Right. So there is another name for this. That's the t distribution with 1 degree of freedom. Right. So here is the graph of the Cauchy distribution. Right. So you can see that it's symmetric around zero. It has kind of a bell shape, but it's more peaked than a normal distribution, more peaked than a normal distribution. And it has the very much longer tails, actually, without coming to zero as quickly as in the normal distribution, right? So these tails don't become close to zero until x goes to negative infinity, and on the right hand side, x goes to positive infinity, right? The densities still become somewhat different from zero, right? So that's what happens. So that's why when we integrate x times fx, right, uh, over the negative infinity to positive infinity region to find out expected value, that doesn't converge, right? The answer becomes infinity, right? So therefore, the expected value doesn't exist, right? And thereby variance also doesn't exist because variance is equal to expected value of x minus mu square, but mu is undefined. So therefore, variance is also undefined in that case. Right. So even though it looks like a normal distribution to some extent, if you compare it with actual standard normal distribution, there will be a much difference, right? If you consider, for example, standard normal distribution, we know that uh, almost all the density is between -3 and +3, right? Only very little area beyond -3 and +3, less than -3 or more than +3. But here you can see that uh, -3 will be somewhere here and +3 will be here, but the density is not even very close, not even close to zero. It's like 0.05 and so on. So it's quite different from the normal distribution. So the Cauchy distribution does not possess a finite mean or finite variance because the corresponding integers diverge, as I just mentioned. Now, there's a very unusual property that is also coming from the previous property. We know that if, for example, uh, if you are considering a sample from a distribution with some finite mean and finite variance, it doesn't have to be normal. It can be any distribution as long as it has a finite mean mu and a finite variance sigma square. Then we know that x bar is also distributed around mu. Expected value of x bar is always equal to mu in that case, if mu exists. And we call it actually the unbiasedness. X bar is called an unbiased estimator for mu. And in particular, more interestingly, we know that the variance of x bar will be sigma square divided by n, right? So variance will be decreasing. Variance of x bar will be decreasing as n is increased in general, right? When the mean and the variance of the parent distribution from which we get x1 up to xn are finite, then the variance of x bar becomes smaller and smaller as n is increased. But in this case, it's not like that. So therefore, actually, in the previous situation, for example, if you just take x's to be, say, gamma, x1 up to xn is gamma, then x bar will be, it will also have a gamma, but not the same gamma as the original gamma. Their parameters will be different. If you take, for example, x1 up to xn to be, say, normal with mean mu and variance sigma square, then the distribution of x bar will be still normal, but the variance will be sigma square n. So it's a different normal distribution in that case. Right. But if you consider the sample mean of Cauchy distribution, sample mean of Cauchy distribution will be the same as the distribution of the original data, right? If you have x1 up to xn IID from a Cauchy distribution, then x bar also follow the same Cauchy distribution. That's a very theoretical and interesting result again, right? Because the variance of variance doesn't exist for the original observations. So therefore, variance doesn't exist for x bar also, and the mean doesn't exist for x bar also, right? So the shape will be the same, and mean doesn't exist, variance doesn't exist. So therefore, it's again a Cauchy distribution like the original parent distribution, right? So that's what I mentioned. This behavior differs fundamentally from distributions with finite mean and finite variance, where the variance of x bar is usually sigma square over n. Right. So, so my battery is down. I have to plug in. Therefore, for the moment, I will stop my recording here. Okay, let's continue. This is another interesting thing. You can transform in the last lecture, actually, I showed you that we can transform uh, uniform random numbers into some other distribution using probability integral transformation, right? So we can do the same here if you want. You can generate Cauchy random numbers from uniform 0, 1 random numbers, right? So what you have to do is you have to get the inverse cumulative distribution function of the Cauchy distribution and apply that inverse cumulative distribution function to the uniform random numbers, right? So when you do that, your transformation will look like this, where U is a uniform random number, random variable. So if you call this quantity as X, right? So this is the uh, inverse cumulative distribution function, that function evaluated at the uniform. And let's call it X, and we can show that X has a Cauchy distribution. Right? So the Cauchy distribution is a particular example in uh, some theories, like, for example, if you talk about central limit theorem, as I mentioned earlier, and then law of large numbers, and other limiting uh, theories don't apply for this distribution. The Cauchy distribution is an important example of a heavy tail distribution and illustrates situations where classical laws such as law of large numbers and variance reduction of averages fail. Right. So therefore usually the Cauchy distribution is considered as an example where those theorems don't apply, or don't the theorems are not valid. Okay, now let us look at another distribution called beta distribution. Right? So if I consider all the distributions, so continuous distributions that I have introduced to you so far, we started with, I think, gamma family, and then we talked about exponential distribution as a particular member of the gamma family, and then also chi-square distribution. Uh, and then today we looked at log-normal distribution. They all are defined on the whole positive real line, right? From 0 to infinity. But there are situations where there are random variables where the domain or the support, we say, where the density is positive, is not the whole real, positive real line, right? It can be only a certain finite interval. The length of the interval can be finite. For example, if you are considering a sample proportion always between 0 and 1, it's a continuous random variable, but it's not going from 0 to infinity, it's from 0 to 1. So if you want to model the sampling distribution of sample proportion, the distributions that we have discussed so far are not suitable, right? Or even if you, for example, consider the marks of students for some subject, usually suppose the marks are between 0 and 100, right? Uh, of course, if the marks are normally distributed, usually marks have a symmetric distribution. Usually people consider normal distribution as a model, because usually in the normal distribution, the density comes to 0, almost 0, when it's between with beyond 3 sigma from the mean, right? But if the, for example, if the distribution of marks is positively skewed, the normal distribution, that kind of distributions are also not suitable, right? Uh, so one suitable model in that kind of situations, that means if the support of the data or the distribution is in a finite interval, meaning the length of the interval is finite, then beta distribution is a suitable model. Right? There's a family of beta distributions. Beta distributions contain two parameters. They are called shape parameters. So depending on their values, the family of beta distributions have a large range of flexible shapes. Generally, we can consider it to be in an interval between some A and B. But here, what I have given you is the standard beta distribution. Standard beta distribution is distributed between 0 and 1. The support is 0, 1 interval. Right? So the beta distribution is a flexible continuous distribution defined on the finite interval 0, 1. Right? So here, actually, to be complete, should have said the standard beta. A generalized beta can be in an interval A, B generally, where A is a real number and B is a real number. It is widely used for modeling proportions, probabilities. That means again, probabilities, not parameters, but again, sample probabilities. And random variables restricted to a bounded interval. Of course, we use beta distributions as the prior distribution of probabilities. In that case, in the Bayesian sense, right? In the classical sense, it is not meaningful to talk about distributions of probabilities because in the classical sense, probabilities are parameters, the random variables. But in Bayesian sense, uh, parameters also assume to have distributions called prior distributions. Right. So in that kind of situations, actually, we use beta distribution as the prior distribution of probability. That's why it's mentioned here, right? Uh, a random variable X is said to follow a beta distribution with parameters alpha and beta, which are both have to be positive. If its density is given by this expression here, where this quantity is the normalizing constant, right? So this quantity has to be there so that the integration of this thing between 0 and 1 to be equal to 1. So that's why we call it the normalizing constant. This is the usual gamma function, right? This alpha and beta both are in this case, you can see that they are appearing as powers of x. And generally that kind of parameters are called shape parameters. Right? So these both alpha and beta in beta distributions are shape parameters. The constant, this constant is the normalizing constant. So as I mentioned, by changing alpha and beta, we can get a large number of shapes. Right? There's a large flexibility of shapes in the family of gamma distributions. Right? So if alpha and beta are equal, then the beta distribution with that one is symmetric, like this, right? Depending on, of course, alpha and beta, whether alpha and beta are equal to 1, or alpha and beta equal to 2, and alpha and beta equal to 3, the distribution will have different shapes, but symmetric like this. Right? So here I have just considered one particular situation where alpha is equal to beta. In alpha is less than beta, then the distribution is skewed to the right. Right? Skewed to the right like this red one. When alpha is less than beta. When alpha is greater than beta, similarly, it's like the mirror image becomes skewed to the left, like the green one. If alpha and beta both are less than 1, then the distribution even becomes U-shape, or sometimes some people call it bathtub shape, U-shape, right? And in addition to that, actually, you can have exponential type distributions, completely starting with somewhere here and then coming down, and then starting with here and coming down. That kind of distributions shapes are also possible. Right? So therefore, you can see that beta distribution in a finite bounded interval can have large range of shapes. So therefore, it's a very good model, especially when the random variable, possible values for the random variable in a bounded interval. And when alpha is equal to beta is equal to 1, we get a particular distribution that is the uniform distribution. So as I mentioned here, when alpha and beta are equal, it will be symmetric, right? Usually it can even become like a normal distribution. I think when alpha is equal to, if I remember correctly, uh, half and half, right? You have to check. I'm not 100% sure about it. But if alpha and beta both are equal to 1, then you get the uniform distribution. In the 0, 1 interval, you can easily see that, because if alpha is equal to 1, this becomes 0, therefore this becomes 1. Then 1 minus alpha, this part will be equal to 1 minus x, this part will be 0, right? So this will be just 1. So this whole thing will be 1. The density will be equal to 1 in the interval 0 and 1. Therefore, it is the uniform distribution, right? So that's a pretty particular case. Yeah, as I mentioned, a beta distribution is can be applied as a model for the density function of random variables which are in a bounded interval, like sample proportion, and also population proportion in the Bayesian context. So the beta distribution is especially important in Bayesian statistics, where it is the conjugate distribution to the binomial distribution. So I will just briefly mention what we mean by the conjugate distribution here. In the uh, Bayesian context, actually, we consider random variables, right? They have some distributions, and the parameters also assume to have some distribution using the prior knowledge about the theta parameter. They are called prior distribution. And you combining these two, usually instead of looking at only the distribution of the random variable x, we usually look at something called the posterior distribution, which is the product of the density function of x and the prior distribution, right? So usually in the Bayesian context, we make inference based on this posterior distribution. But what happens is, actually, if the density function, the form of the density function and the prior distribution are quite different, then the product of those two becomes very, very complex. And therefore, the posterior distribution becomes very complex, the form of the posterior distribution. And therefore, finding the expected value, variance, and like that, if you want to find out the probability, integrating that will be usually difficult, right? So therefore, as a mathematical convenience, people try to find out, when they consider the prior distribution uh, in the mathematical form, very similar to the uh, density function, so that the product will be very simple, like in the prior distribution. So that kind of prior distribution that we select is called a conjugate prior. So for example, suppose we are assuming that x has a binomial distribution with some number of priors equal to n, and probability of success equal to p, right? Here I'm using p instead of theta as in the usual sense, because I'm going to assume later on p itself has a random variable distribution. Therefore, I'm going to consider it as a random variable. right? So in that case, X has a binomial distribution. Therefore, the mass function of X has this form. Of course, it's proportional to this. There will be NCX term, but here it's not important for us because we are just going to look at the product of those two and then select the proportionality constant so that the posterior will be actually density function. So this proportionality constant is not that important when you are considering this uh, Bayesian uh, uh, distribution of X, Bayesian context, right? And similarly, now the posterior distribution will be equal to then this mass function times whatever the prior distribution that we assume for P, right? So what we are aiming is the product to be also in this form, right? The product also will be in this form if the density that we are going to assume for the as the prior distribution for the P sample proportion is also in the same form, right? So we can therefore take, of course, P, we know that is going to be between 0 and 1, is continuous. So therefore we have to have a continuous prior distribution in the interval 0, 1 with the same form as in the binomial distribution. So the best thing we can consider it as in that case is a beta distribution, which has this form with some values alpha and beta. In this case, we will have to assume some known values because it's coming from prior knowledge, right? Usually alpha and beta will be known values, right? So as a result, when you consider the posterior distribution, it will also be a beta distribution with some parameters like this. The product will also contain P and then 1 minus P, and the powers will be only different. So, but still, it has the form of the beta distribution. So we can select the uh, normalizing constant accordingly so that the integration over 0, 1 will be equal to 1, right? So when we do that, we can show that the P, the prior, the posterior distribution of P, given the sample x equal to x, will be beta distribution with these two parameters. If we consider P to be, if we consider the prior distribution of P to be a beta distribution. So that's why we call it the conjugate prior, right? That prior gives you the posterior in the same form as the likelihood function or the density function of x, right? So this will be discussed more if we discuss Bayesian inference later on, right? Now, at the beginning, I told you that the density function I showed you was actually the density function of the standard beta distribution. This is the standard beta distribution, right? But practically, we may want to consider a general interval, like marks are in the 0, 100 interval. Or you can still use the standard beta distribution if you just divide the marks by 100, right? So then everything will be in 0 in 1 interval, right? So that's one thing you can do if your data are in an interval A, B, then of course you can easily convert them into 0 to the interval 0, 1, and then model those using the standard beta distribution and answer whatever the questions accordingly. Or you can actually consider the beta distribution in that original interval A, B, right? So in that case, we can, if you want, for example, suppose X has a standard beta and you want a beta distribution in the interval A from A to B, then you can use this transformation, right? Y is equal to A plus B minus A times X. And the new random variable Y will be a beta distribution, will have a beta distribution in the interval A, B. So that's a linear transformation which gives you the general or generalized beta distribution. And then let me discuss the last distribution that I'm going to discuss here, Laplace distribution. It's also called double exponential distribution, Laplace or double exponential. So this is a continuous distribution again, defined on the entire real line from minus infinity to plus infinity. And it's also has some, I mean, one might say it's symmetric and some bell shape, but in the middle, it's not actually a bell, it's like a spike. So the density function of the Laplace or double exponential distribution is given by this expression here. It has two parameters again, mu and lambda. So in this case, mu is the location parameter, lambda is the scale parameter. Here, actually, this is the absolute value. Right. So if you want, you can define this as two parts, right? When x is positive, then it's going to be, if x is greater than mu, this will be just x minus mu. If x less than mu, then this part can be considered as negative x minus mu and so on. You can define it two ways, or you can just define like this using just one part, one function, right? So this is the density function. Mu is the location, lambda is the scale parameter, and this is the density function, right? For different lambda values here, I have considered the same location parameter 2 here, right? So you can see that the distribution is symmetric around mu, right? So we might not call it a bell shape because it's not really a bell. It's like a spike at that point, but symmetric, right? So on the other way that you will recognize, for example, if you look at this part only, it's like an exponential distribution, right? Exponential distribution. So this is the mirror image of that. So it's like putting two exponentials side by side. So that's why we call it a double exponential distribution, right? Laplace or double exponential. The Laplace density is symmetric around mu and has the sharp peak at the center than the normal distribution. The density is not differentiable at the peak at x equal to mu because of the absolute value function. It's not a differentiable function at that point, the other point, right? Uh, The distribution may also be viewed as two exponential densities joined symmetrically, or that's what I just mentioned. That's why we call it the double exponential distribution. The Laplace distribution has heavier tails than the normal distribution, meaning that extreme observations are more likely to occur. It is therefore usual in applications involving sharp peaks and occasional large deviations. Right. So that's a very brief discussion about the Laplace or double exponential distribution. So I will stop this part of this lecture here and then continue the other parts in two more sessions, each roughly 1 hour length. The next part in the next part, we will discuss a new topic called entropy.